Hi, everyone. Thanks for joining this episode or edition of Reline Live. I am here with Mike Whitehouse of ISCO Industries / SnapTite liner pipe. He is one of their top technical guys. He pretty much knows everything inside and out from what I've gathered from Mike. I'm going to let him kick it off. He has a lot to get through for you guys, talking about grout, talking about load charts. We have a lot of questions that you guys already submitted, which is awesome. So please feel free to use the question box to submit them. We do have a lot already. A couple of them we know are going to take a while. So Mike and I decided we're going to hold them until the end. But as you chat them in, I'll kind of decide if we should hold them to the end or if I will interrupt Mike and have him answer it on the spot. Kick it off, Mike.
Yeah, thanks, Cassie. Really appreciate it. And thanks to Treasure Valley and Reline Live for the opportunity. It's an honor to be here. And I'm delighted at the opportunity. I want to especially thank all of our attendees. So we're here to talk about grout and how grout density can influence the design and the installation approach used when you rehabilitate a culvert using a slip line product, specifically with the SnapTite. And while this presentation is really geared more towards gravity flow applications, a lot of the principles could be carried over into a pressure pipe application or other slip lining rehabilitation where the annulus is filled with grout. But just a little background on me. I'm not a big titles and guy, but I've started with ISCO in 1994. Prior to that, I put in fiber cable with AT&T. I installed a little over 2,000 miles of fiber cable in the ground, a lot of it by directional drilling, bored under the Mississippi River in Memphis in the late or the early 90s. I've been involved with SnapTite for about 20 years now. I do serve with PPI, or the Plastics Pipe Institute, on their education committee. I'm involved with a number of standards and codes groups, and I'm also actively working with the Corps of Engineers on their manual to rehabilitate culverts in dams and levees. And then this is much of the same information just in my LinkedIn page or profile page. If you'd like to connect with me, I'd love to connect with folks there. And Zig Ziglar was a person I used to listen to a lot and still do. And one of the things that he talks about is keeping the main thing is the main thing. And even when you're talking about other things that affect the main thing has to be the thing that you're keeping in mind. So really what we're trying to do here, the main thing we're trying to address is an existing culvert that has failed. And that failure may have voids in the host pipe. And that allows for infiltration and exfiltration in the host. And that can lead to soils being transported or piped into the host pipe and carried away. And these voids can then lead to potholes or even failures in the road. And if you have an overtopping condition, they can even take out the entire roadbed. So what we're trying to do is find a very economical approach to save the county money or the city money, the Corps money, whoever the client is. We want to do it in a manner that addresses these voids and protects the road. And we want to do it with a product that has a long lifespan. And polyethylene has been shown to have a 100-year service life in water piping. So it seems to be logical that it would have more than a 100-year service life in a culvert application. So ultimately, the solution may outlast your road. The things that we need to do here first are to evaluate, and that evaluation can be an assessment on the existing pipe or the risk associated with failure of the existing pipe. It is based on the loads or the flow that goes into the pipe. And generally, when you have a pipe failure or an aqueduct system failure, it's because your loads or demands have exceeded the capacity of your pipe system. So we want to look at the loads in the flow. And if things are favorable for success there, then the next thing you will do is to move into the planning and preparation stage. And that's where you start to do your surveys. You may install runners or rails on the bottom to help with friction installing the pipe. We cover that in our handbook or design manual. You'll install some fill tubes and some air ports in the host pipe. And then you'll actually bring in the product and start the installation process. With the SnapTite, which we use a mechanical joining system, often is joined with a pair of come-alongs. Sometimes you can use an excavator to walk the pipe back and forth and snap it together. You may need to adjust your grout densities based on your loading designs. You may have to put some inlet control to meet hydraulic demands. But at the end of the day, you rehabilitate the system and you gain the benefits of having a long-term solution, free-flowing, that also helps to protect and keep the road surface in proper function.
Real quick, Mike.
Sure, Kathy.
RPS. That's an acronym that is, I think, specific to SnapTite, correct?
Yes, thank you. The grout plays one component in a total composite pipe system. And in our manual, you will see that we refer to the SnapTite as a rehabilitated pipe system, or an RPS solution. So the grout is just one component in that RPS system. The liner is one component. The hose is one component. Even the soils that surround the existing hose pipe, again, is a component in that RPS. So back in the early 90s, ISCO really, we would supply the pipe and we would say it's up to the contractor and it's up to the engineer or the installer to take the grouting process. And we really saw grout as a problem or an enemy, because anytime we had problems on a rehabilitation project, it was usually directly related to the grouting process. And we found that the contractors and specifiers often lacked a thorough understanding of it, and ISCO actually lacked a thorough understanding of it. Many people felt you bring a truck out, it's full of concrete, and that was basically what we were thinking is concrete, and you pump it in the annular space. What could go wrong? Well, there's really a lot of things that can go wrong, and we'll cover some of those. So that led to a decision by ISCO to really enter the grouting business. And Dudley Burwell, who was a mentor of mine and worked with ISCO, he created our first grouting program in the mid-90s. And when he retired in the early 2000s, I assumed the responsibility for that program. Now, through better understanding, we really see grout as a friend, and we might even date some grouts, but we're really married to none. And we're not going to tell a contractor or an owner that they have to use one grout or another, but there are reasons why this grout might be the one that we want to take to the prom dance, and we'll look at those as we go through the rest of the slides here. But you'll notice here that we're using very low density grouts, and they do require a foam generator. Now, here is a general rule for grout densities, and generally, if you're at 90 pounds per cubic foot, and when I talk about grout weights through the entire presentation, they're going to be in pounds per cubic feet. 90 pounds unless you're really in a cellular grout range. If you're over at 115 and above, you're really more in a flowable fill or even a true concrete. And then between 95 and 115, people often call those a reduced density fill. Now, if you use admixtures such as BASF and RealCell and those kind of deals, they're relying on a chemical reaction process to put air or voids inside that flowable fill. And you're really going to have problems getting below 100 to 110 pounds per cubic foot using those bag mixtures from my experience. As a general rule, as your grout density increases, your compressive strength is going to increase. Your viscosity increases, which means that a higher density grout is harder to pour or place. People call it a slump when they're talking about concrete. Your head pressure on the bulkhead is going to increase as your grout pressure or density increases. And then the hydrostatic load on the pipe itself is going to increase as your density increases. Conversely, if your density goes down, your compressive strength goes down, the grout becomes more fluidic, it's easier to pour in place, and your pressures go down on the head walls and on the pipe itself. I'm going to save the compressive strength for last. I want to get kind of the best for last. So we'll first jump into viscosity. So when you're trying to address the main thing here, part of what we want to do is fill these voids that have opened up around the existing hose pipe. And the best way to do that is to get your grout to flow into those open spaces and voids. You've also got to transport your pipe down these fill tubes, and sometimes those fill tubes can be hundreds of feet long. And I think it's pretty obvious that a grout that is less viscous and flows easier is going to be able to enter these voids and also be easier to transport through your fill tubes. And if there's anybody that thinks that a stiff grout product is better to use in this installation, let's talk after class, because I think you must understand something that I'm just not getting here. The next one we wanted to talk about is the head pressure that occurs on the bulkhead during the grout placement. And in this RPS system, your bulkhead becomes a structural member during the installation process. So here I've got a couple jugs, and they hold 48 ounces. One of them has 12 ounces or 16 ounces in it. One of them has 32 ounces in it. So this one's 1/3 full. This one's 2/3 full. And you can see that the 2/3 full, when you reach equilibrium, it creates more head pressure on that bulkhead. But now if I put just a little bit of slope to this pipe that's only 1/3 full, now I've got the same or more head pressure against that bulkhead. And again, I think everybody agrees we don't want to have frac outs in our system and have things escape. We want to keep that grout inside the annulus. And we've also got a liner pipe here that's inside there as well. And we've got to be cognizant of exceeding the capacity of that liner. And that's really what comes in. Yes, Cassie, thank you.
You move on. Could we go one slide back? I just thought of something that I'm curious on.
Sure.
So we'll move back from here. So because you're putting the grout tubes inside the hose pipe, between the liner and the hose pipe, do you assume that these voids is because there's damage to the hose pipe, and so the grout will go out through the hose pipe and fill those voids? Is that just an assumption we make?
Okay. That is the assumption made. In order for infiltration and exfiltration to occur in the existing conduit or culvert, there has to be openings or voids there for the soils or the fill to get in. And then you're using those same voids to try to pump your grout out.
Perfect.
And
all right.
We've done some studies using ground penetrating radar, using isotopes and x-rays, and also through dig-ups that provide a lot of confidence that we are indeed getting to these external voids. And that's a key part to maintaining the road surface, because it's one thing to put a liner or a Band-Aid inside your host culvert, but if you don't do anything to address the materials that have been removed from around the host, you really haven't solved the problem of the road, and it's going to continue to settle and fail. So that's a great question.
Okay.
So here we're looking at the allowable hydrostatic pressure that you can put on a polyethylene pipe. And these equations come right out of Chapter 6 of the PPI handbook. They do take into effect the ovality that's present in the pipe. If you have a perfectly round pipe, you're going to have more and more force vectors that are tangential to the pipe than you do that are normal or perpendicular. If that pipe becomes oval or out of round, you're going to have more and more force vectors that are perpendicular and less that are tangential. The other thing that comes into play is the E, or the modulus of elasticity. And in this application, the modulus of elasticity for your pipe is controlled by the heat of hydration. And the way that we determine the heat of hydration is putting a thermometer in our admix, or in our grout mixes that records the minimum and maximum. And when we do that, we found that 120 degrees F was the maximum curing temperature that is produced with the foam generator products. If you go back to the admixtures, again, you're relying on a chemical reaction to produce the air that goes into the flowable fill to create your lighter density grouts. And those chemical reactions are often exothermic. So you may warm the pipe greater using some of the bag mixtures. So your heat of hydration is going to control the modules that you use for evaluation. And we also apply a safety factor of 2 to 1. And when we run the math here and we use a short-term modulus at 120 degrees F, we find that the load limit for this liner pipe is about 2 PSI to prevent buckle. And again, that's at a 2 to 1 safety factor. So that's where we come up with our recommendations in the design guide to limit your pressures to 2 PSI. And really, most first graders get this concept. They know that if they take a straw and stick it in a really thick milkshake and they try to drink it, that straw is just going to collapse on them. They know that how thick that milkshake is pretty important to how hard they can suck on that straw. But yet, as designers and as installers, sometimes we tend to forget that lesson. Well, here's a slide that Don LeBlanc presented with DL views in his discussion on grout. And Don's obviously as smart as a first grader. He's pointing out here that when we use a low density cellular grout, that you're really helping to mitigate the pressures that might happen on your bulkhead and that might happen on your host pipe or your liner pipe.
Yeah, so
he's also pointing out.
Mike, I have a really good question, and I think it's perfect for this slide. So one of the attendees typed in, when grouting, if there are significant voids above the pipe and above the level of the grout tube, while pumping at a low pressure so as not to exceed the 2 PSI, 2 to 5, will the voids above the pipe get filled with grout, or should we assume we need to fill another method? And I kind of asked this, I think this is along those same lines, but if there are a lot of voids, is his point valid that it won't be, and it's very low pressure, that it won't get out to those voids, and then maybe there should be something else considered to fill them?
Sure, it's all a matter of physics. Most of this boils down that the physics is a lot of engineering work, and you've got to have enough pressure, whether that's through pumping or through elevation and head pressure, to be able to get that fluid to reach an equal level to get up into those voids. Okay. When we've done the dig ups, we found that a lot of those voids are truly filled, but there is a hydrostatic level there. If your void's much higher than what your grout elevations are, then that can be an issue. And we've also seen people that will actually put a 90-degree elbow on the bulkhead as it comes out, and they'll create a standpipe. And that standpipe will help create head pressure to push the grout up into those higher elevations. But again, you need to be careful not to exceed the buckle pressure on your liner.
Okay.
Now, these conditions that I have here are pretty conservative. And when ISCO asked us to create a grouting program, our directives were to come up with something that was repeatable, that we could do reliably across the nation and not have concerns that we're going to exceed the limits of the pipe. So this is kind of like the Dave Ramsey program. This may not be the only method to get you out of debt, but this has worked for tens of thousands of applications, and we have a lot of confidence in it. Now, does your grout provide more support to that pipe than true water or liquid does? Likely so. Does all the heat go into the pipe? Well, you got a big heat sink around it, and from my studies, most of the heat of hydration does go through the pipe. But some of these may be a bit conservative. And again, owners, engineers, contractors, they can adjust this equation to what they feel is best and most appropriate for their projects. So again, looking here at Don's, he's pointing out that not only do you have more pressure on your bulkheads, and not only do you have more pressure on the pipe, but you also have more buoyancy. If you create a higher density fluid, you're going to have more force up on the pipe. And where he really points out the key part is your required compressive strength in your grout only has to be as strong as the surrounding field that's around the host. That's all we're doing. If you hire a contractor to put in the dig and replace this conduit, you're going to have them put in a piece of corrugated pipe or a piece of plastic pipe or a piece of metal pipe or concrete pipe. You aren't going to have them pour a 3,000 or 5,000 PSI bridge deck around that installed pipe. So here we're looking at the grouts that we promote: 40 pound, 55 pound, 75 pound. Here we're showing that the published compressive strengths, and here we're trying to equate it to a Young's modulus. Most of your road beds have a 3,000 or a 4,000 PSI modulus. So even with our 40-pound fill, we're creating a grout in that annular space that is as strong or stronger than the surrounding fill. And these do use a foam generator. That foam generator uses a wetting agent and an air compressor to create air bubbles. And those air bubbles basically replace the solid aggregates that are in the grout mix. And that does require an investment. And some contractors and some installers say, why do I want to invest in a foaming machine? Well, let's look at this loading table. It's real easy to take your grout density, again, pounds per cubic foot, and if you know the height of the lip that you're going to be pouring, and we know a 2 psi pressure is where we have a 2-to-1 safety factor. So everything on this white and yellow line is basically our limits for a 2-to-1 safety. Everything in the yellow is where we're beginning to encroach on our safety factor and approach the limit of buckle based on the design parameters that I've used in the unconstrained buckle equation. And we can see here with a 40-pound grout, I can go down 7 feet deep before I ever have to really worry about getting to my limit at a 2-to-1 safety factor. And I can go down 14 or 15 feet deep before I'm really ever concerned that I'm reaching the limits of that liner pipe. Now, if I get over here in 100, 120 pounds per cubic foot, when I go 2 feet, I've reached 2 psi. I'm at my safety factor. And if I go to 4 or 5 feet, I'm now at a risk of buckling the pipe. So once you decide on a density that you want to use for your project, quality control is obviously important, and you can do that by weighing the amount of material in a known volume. Or another thing you can do is create density blocks, and those blocks can have the same density as the grout that you're trying to formulate. You put the block inside of the grout. If it floats really high, your grout's still too dense. You need to put more air in it. If the block just floats right at the surface, and then you've reached your target density. So like I said, I wanted to save the best for last, and let's look at the compressive strength and how it affects loading. But we're getting close up to the 30-minute mark, so I'm going to move really quick here. But again, as the grout density increases, your compressive strength increases. And we're using LFRD methodology for all of our evaluations. And these are the consultants that we've used in the past and still currently use to help us. And I can't thank our consultants enough for the education and the understanding that they've given to us. This is a white paper that was presented by Don LeBlanc and Don McGriff and Tim Tolliver to the TRB in DC just earlier this year. And what we're doing is we're analyzing a 63-inch liner pipe that's put inside a 72-inch host. And we're using Candy as the evaluation method and also LFRD for a double check. And this is a very robust finite element analysis program. This isn't something that you download from the Apple Store. The user's guide for this is 3,000 or 4,000 pages long. Dr. Katona came in and spent 3 or 4 days with us to train us how to use the FEA software. Each color represents a different material, so you can design different properties for each fill material used and for each material used in the RPS system, the liner pipe, the host pipe, and the grout. When we're doing the evaluation, we assume a frictionless interface between the grout and the host, and between the grout and the liner. And we know that friction does occur, so that makes this a very conservative analysis. We can also allow for modeling for H20 and H25 traffic loads. And when we go through the LFRD analysis, we're entering these as our compressive strengths. And I asked how we knew those were the compressive strengths for the grout formulations, and they said, well, that's what the manufacturer tells us. Well, I'm like Harvey Svetlik, a good friend and mentor of mine, and God we trust, everybody else we double check. So I went out and had Patriot Engineering double check our 28-day break strengths. And for a 40-pound grout, we're advertising 375, and they came in at about 380. For a 75-pound grout, we're advertising 1,500, and we came in almost double that with our third-party evaluation. Patriot was really amazed that we were able achieve that compressive break strength with a cellular grout. And when we use these LFRD analysis and these compressive load ratings, we come up with allowable burial depths in the RPS system that go to over 100 feet sometimes when we're using good soils being 3,000 PSI modulus or higher, and using a high strength grout. Even in a poor soil with a medium strength 55-pound grout, we can get 50 feet or even close to 100 feet burial depth with good soils. Most of the applications we enter are less than 50 feet deep. They're 25 to 50 feet deep. And those applications, the analysis from Candy and from LFRD shows that we have the capacity to meet those demands. When you look at shallow burial and the ability to handle the traffic loads, again, 1 foot to 1.5 foot of burial above the top crown of the hose pipe is all that we need to have sufficient capacity to handle those demands. So, you know, if 2 aspirin cure your headache, why take a whole bottle? Or why take multiple bottles? If you take multiple bottles of aspirin, you might put yourself in a hospital, you know. And if you start taking multiple bottles of aspirin, you start specifying really high density grouts because you want a 3,000 or a 5,000 PSI compressive strength, you're really putting the liner in the RPS solution at some risk. And you're doing that without really gaining any benefit for the allowable loading conditions. And again, in conclusions, Candy and the LFRD methodology clearly show that we have the capacity to handle these demands. And the lower density grouts have other benefits to the composite system beyond just the loading that we've talked about. And these are just some general philosophies of mine. I'm dedicated to providing sustainable piping solutions for infrastructure. I believe in building a better tomorrow through improved infrastructure today. And I look at providing a total system solution and not just a product. And these are some checklists that Don LeBlanc had in his presentations. These come from CDOT. One thing that I noticed that's not in here that you might want to consider, I think Don LeBlanc, you may be out there listening, CDOT may be as well, is this doesn't cover the heat of hydration. And really that's going to come into play with some of these other items here. And then at the bottom, it says certifying that the grouting plan conforms with all provision, costs, and restrictions of the liner manufacturer. Well, that's going to be really hard for me as a liner manufacturer to do, because I don't know the admixtures and the chemical properties and the heat of hydration of the grouts that other people might want to formulate or might want to use. They're welcome to use those, but I can't confirm or validate their grout programs. The only grout programs that I can confirm or validate are the ones that ISCO have created. And with that, I'll open up to other questions and thoughts and just kind of leave this one up for our checklist. Cassie, what do you have for me?
So how long does the grout
on time? Yeah. Just barely.
Yeah, we might go a little over with we've got some good questions. How long does the grout take to set up, and could heavy rain be a concern?
Again, how long the grout takes to set up is going to be a function of the formulation or the mixture that you use. And typically, grouts will begin to set or begin to provide structural support to the liner where it's not in a truly fluidic nature, but more in a semi-solid nature within 3 or 4 hours. Generally, when you pour concrete, you can walk on it within 24 or 48 hours afterwards. So it obviously has a lot of set and strength properties just in the first 24 hours. Now, concrete does continue to cure sometimes up to years, but it basically reaches most of its curing process within about 28 days. And that is why most of your compressive strength calculations and design calculations are based on a 28-day break strength. Because by the time it gets to 28 days, it's achieved basically 99% of the strength that it's ever going to have. And then from there, the chemical reaction is very slow.
Okay.
As far as rains, that's going to be a tricky question. And first, hopefully, you're able to schedule your work around weather events. If the bulkheads are secure, and if you have grout tubes that are injecting the pipe, similar to what we showed towards the beginning.
Yeah.
Really, the only way for rainwater to get into the system is to get into the ground, and then from the ground to enter those same voids that might be in the hose pipe to get in. And if you have that, then you may want to wait to place the grout on another day. Something else to consider, and we point this out on the grout table, where we're talking about densities. Down here at the bottom, water has a unit weight of about 62.4 pounds per cubic feet. So if I'm using a 40-pound grout and there's water in that annular space, basically what I'm doing is putting oil on top of that water. My grout's less dense than the water, so the grout is going to float on top. That's not an ideal situation. So if you have groundwater present, that's where we might really push designers and installers back to a 75 PSI grout. So you may use a heavier grout to displace groundwater as much as you might for load strength.
Gotcha.
And hopefully that covers the questions that came in.
Yeah, I think that's good. So one question is long, so I'm gonna read everything that was written. HDPE has high expansion and contraction properties. Should a cement-based grout be used for backfilling the annular space between the hose pipe and the new carrier pipe, where the pipe emerges from the concrete grout? Total axle bending stresses are set up that may contribute to long-term rupture at that point. Others have recommended the use of a compressible membrane around the pipe, which then allows the pipe to strain naturally and avoids the issue. Wow.
Okay. Yeah. First, we'll talk about thermal expansion and contraction, and polyethylene does have a very high expansion and contraction rate. A good rule of thumb is it's going to grow 1 inch for every 100 feet for every 10 degree a temperature change. Obviously, you are putting some heat into the system when you pour the grout because it has an exothermic reaction. Typically, there will be enough frictional interface between the pipe and the grout once it is cured to limit axial movement. If that is a concern, you can certainly put flex restraints or wall anchors on the terminating ends of your pipe, and then you can cast those into your bulkhead. And then your bulkhead becomes a structural member that, number one, helps to hold your grout inside the annulus, and then it becomes a structural member, number two, to prevent movement of the pipe during thermal expansion and contraction or temperature changes. As far as a flexible seal around the opening, people are welcome to use those, but the first thing you have to remember though is that seal will still need to be able to maintain your grout as you're placing it in so that it doesn't leak out between the host and the liner pipe. The polyethylene is a very elastic material, and it has a high degree of allowable strain. In the seismic committee that I'm working on with ASCE, we're looking at 5% allowable strains or bending due to earth movements. And there's strong evidence done by EPRI and others that shows that 10% allowable strains may even be acceptable for the polyethylene material. So again, every material is going to have its limit, but the polyethylene material is very ductile, it's very flexible, and it should handle bending better than more rigid pipe materials such as fiberglass, cured in place liners, or possibly even concrete. Obviously, the loading reactions will be different with each material.
Right.
Hopefully that addresses that question. If not, my contact information is at the beginning and end of this. Love to have conversations with people. I'll even come visit you once we get travel restrictions taken off.
Last question I think that we have, unless someone wants to type something else in, and then this should wrap us up, is, and you and I got this one in advance, so we knew it was coming. What is the effective modulus of passive soil resistance at 44 PCF foam grout?
That's one that I'm going to need to research and get into. I've learned not to answer a question that I don't have high confidence that I know the answer to already. And I've learned in technical support that it's much better to give absolutely no support than incorrect technical support. So I would want to research that a little bit. I do have tables that help to They're in chapter 6 and 7 of the PPI handbook to equate modulus to different fill materials at different compaction levels, but I'm not sure we have it completely for the grout. So probably the closest thing that we have is in our load table here, where we're equating compressive strength and grout densities to a Young's modulus. But this is a difficult question to answer geotechnically.
Okay.
Yeah.
Well, unless anyone else has any questions, which I haven't seen any more come into the chat box, I think we did a great job. We only went 7 minutes over.
Well, thanks. Again, I really appreciate the opportunity to be here, and especially appreciate those who attended to listen to the message and how we came up with the grout formulations that we promote in the design guide. And again, feel free to reach out to Cassie, TV Pipe, to myself, members of the SnapTite team, or anybody at ISCO. We'd love to help you with solutions to the challenges and problems that you're facing.
Yeah, we really appreciate you guys joining. Reline Live seems to keep picking up steam, and the grout seems to be one of the hottest topics. So we get a lot of registrations on this one. So we might be bringing Mike back for round 2. We'll see. Just when you guys get your thank you email, respond to me. Let me know what topics you guys want to hear about. If you have ideas, if you have things that you want to hear about, that's what I need to know so I can bring on the right speakers and hosts. Thank you guys. Have a wonderful Thursday, almost to the weekend. Bye, Mike. Thank you so much.
Thanks, everybody. Have a great day. Be safe.